Hey everybody, this is Larry, this is me going with Q4 of the bi-weekly contest 163, minimum cost path with teleportation. Hit the like button and subscribe button, join me on Discord, let me know what you think about this one. This one I actually end up taking about 20 or 18 minutes or whatever it is. Honestly, if you watch the live portion, I even called it out during the live recording. I was like, after 4 minutes, I knew exactly what I need to do. And then it just took me a while, I don't know, maybe I'm slow these days, and just typing it out and having typos, etc. But the idea is, we'll go with the idea. I think there's a DP. I mean, I've seen some DP solutions. I didn't think about it that deeply yet. Maybe it's necessary, maybe it's not. But I didn't do it with DP. I did it with Dijkstra. Maybe some part of the reason is because Q3 was a Dijkstra problem, and as a result, I looked at it. I'm like, oh, the balance makes sense for Dijkstra. Let's just do it with Dijkstra, right? Pretty straightforward idea. Yeah. And if you haven't already guessed, this is a shortest path problem, where greedy works, right? I mean, you have to do it greedy correctly, but it works, which is how Dijkstra works. So the first thing to notice is that RNC, I call it RNC, none of this M and N confusing crap, is 80, right? So 80 square is, 6,400 if you want to be precise, times 10, which is fine, 60,000. So you cannot do R, you cannot do R times C square, or R squared times C squared if you want to be more precise with the parens, right? So you have to be a little bit smart, right? Because of this relationship of teleportation, if you're not careful, you would, even if you don't relax, the number of edges could be R squared times C squared, right? Over 2, maybe, just pointing in one direction or whatever. But if you're not careful, and that is really the hard part about this problem, is kind of deduping, if you will, that part of the math, right? Because if you just want a naive Dijkstra, you will time out because there's just too many edges. So how do you do it? Well, the key observation to note for this problem is that, well, there's the K thing, we can handle K later, but it's that this relationship, right? And how it deals with greedy. How it deals with greedy is that I'm going to bring up a drawing board. Hang on. Oh, they don't have any grid for me to draw on directly, so we have to create our own. Because often I just copy and paste a grid that they have an example on, but today for some reason I guess they're lazy on the grid. But in any case, you have a grid, right? Let's draw it a little bit nicer because I have the right numbers in it for this one, right? Right. So you have a grid. Let's just put some numbers, right? I don't know. And without loss of a generality for now, let's just ignore K for now, right? No K, no worry about K, because that's not, for me, that wasn't the hard part of the problem. You could, for reasons of maths, because R times C times K is small enough, like I said, I think it was 64,000 or something, or maybe times 1 more, so it's like, I don't know, times 11 instead of 10, but either way, something like that, right? Which is not that many states, right? If you don't do the n square edge thing. So the idea is that, okay, let's say you have a grid. The hard part is that if you do an explicit graph, like for example, you look at this one is the smallest number on the thing, so literally every other number you can jump to this number, right? And that's a lot of edges if you kind of do them a lot over time. So the idea here is that in a greedy way, what am I doing? What do I want to do? What you notice with that relationship about numbers that are smaller, well, is that, okay, you notice that, let's say we're at this here, right? Again, we skip the K conversation for now. It's not the hard part, right? But let's say we're processing this node. We're here. What does that mean? Well, here, that means that, okay, so if we're at a node 5, what does that mean? That means that if the path to here, if the path here, the shortest path in a greedy way, then if we're able to hit a number, we would have already done it. Don't know if that makes sense. It's a little bit confusing. It's a little bit confusing to say. What I mean by that is that okay, let's pretend this 5. We went, you know, from 1 to 5. That seems like a shortest path, reasonable, maybe in the way that there's some because this is teleport, so a little bit confusing. But what I mean by that, maybe that is actually not bad, right? Because we already did. I mean, we already did 5, but let's change this to a 6 for now, right? Because I didn't really think it long enough as an example. That means that we did 1, 2, we did 6, and then we did a 5, right? What does that mean? That means that we are trying to hit all numbers less than 5, or equal to, I guess in this case, to teleport to. But we know that we visited a 6, right? Because we visited a 6, we also know that we want to already hit all the numbers that are less than or equal to a 6 to teleport to, right? Because it's free, etc., right? So that means that we are at 5, we don't want to repeat them because it will never give you a better answer because you already did it, right? Like if you could have gone there for cheaper, you have already teleported. So the only case is that you go there but worse or slower, right? So that's kind of like the idea that I want to build around, is that you don't well, there are 2 things. One is that you know you don't visit them, but you also want to do things in a way such that you don't even consider them, right? Because okay, like in this case, maybe we'll say like, okay, let's say you have another cell, like this 6, we know that we could teleport to this 2 and this 1, this 3, right? This 3 ... We know that, well, yeah, obviously we know that we can go from 5, we don't want to go to 1, we don't want to go to 2, we don't want to go to 3, but even though you know that it won't give you a better result, if we did a linear check, it will still time out because now you're doing these checks. So what you want to do instead is just skip, right? Here maybe we know that we already done these, so we don't process them at all as a 5. Let's change some inputs for a second, right? And what I mean by that is let's change this to a 4. In this case, I forgot what color this is. In this case, we still visit everything, right, that we pointed to, but where's the 5? Okay, but here we know that we haven't. So then basically the idea is that we just want to construct a way for us to skip checking here, but we skip, like we go, okay, well, this 5, let's check here, because we know that the previous number was a 4, the previous biggest number that we tried was a 4, so we want to check the numbers from 4 to 5, right? And that's basically the idea for this problem, is just constructing either a data structure, if you want to call it that, or just bookkeeping, or if you want to call it that, or depending on which way you implement it, right? And by bookkeeping, I mean just like keeping track of all these things, like the way that we said here. Maybe we'll say, okay, the previous number that we've been to is a 4, keep track of that so we don't do it again, etc., right? Okay. So with our K, so let's say we didn't, like, our example initially is that we don't care about Ks, right? In terms of number of visits, then you would just have this in a global state, right? You have this in a global state of, okay, we visited, you know, like maybe you would just have a counter that's like, oh, here we visited, the biggest number that we visited before is a 4, so here we just go from 4 to 5, and then now we update the biggest number to a 5, right? So that the next time, let's say we're at 7, we don't do numbers smaller than 5, right? Or equal to 5, right? But you do have a K. So what do? Well, there are probably proofs that you can do, honestly, to kind of even update it more. But for me, the lazy thing for me to realize, the thing that I realize that I know is true, but maybe I could have done more, is that for the same k, we just have a state for each k. What I mean by that is that for each k, for example, if k is equal to 2 and k is equal to 1, you could count upwards or downwards. It doesn't, we just have to not go over or under or whatever. For each of these k, we just keep track of the biggest number that you go to, kind of. You could do this in a number of ways, like I said, and I'll show you my way that I did it coming up. But you could be like, okay, with k is equal to 2, the max number that we process is a 4. Maybe for k is equal to 1, the max number that we process is a 6. So that you kind of keep on track, so that instead of going like, okay, well, you have this 5, you don't want to, like I said, you don't want to check this, you want to check this. You want to skip all the way to 5 to check 5 directly. In that way, if you amortize it out, that means that for each number, for each cell, you only check once. Positively. I mean, maybe you check it negatively, but inside, like if it's forced, then you just kind of end the loop early, kind of thing, right? So yeah, so that is basically the core part of this idea. Is this like you have an implicit graph, you don't have enough time in this case, or maybe even memory, to create an explicit graph. It is based on this ordering thing that allows us to, amortize out the cost. And that's basically the idea for this problem. And we'll go over it in code. I think once, and like I said, I realized and recognized all this in about like 4 to 5 minutes. Implementation took a little bit longer, but again, most of this code is going to be Dijkstra. So definitely familiarize yourself with Dijkstra. Right, in terms of having the states and stuff, and just I'm not gonna go with Dijkstra in super detail. I'm just gonna go over the changes I made to make it happen. The first thing is noting that we don't, and this part is standard, but I didn't go over it deeply, which is that for every cell, we have k different ways of reaching it, right? Meaning that you can reach the cell with the lowest cost using 0k, using 1k, using 2k, using 3k, using 3 teleports is what I mean by using k, right? And so forth. And all of them could be different, right? Meaning that maybe I teleport once to save on cost, but later I needed that teleport, so you want to consider all the possibilities, and this is the way you do it, is by creating an extra dimension. And this is why I talk about R times C times K earlier, because then that just creates a number of unique states, right? So this is what I have here. And this, once you realize that, it's still a standard Dijkstra, but I guess it's not if you have to think about how this state. But this part, it does come up, maybe not for not necessarily teleports, but this idea of like having k resources or whatever does come up often. So you have to think about whether it applies and whether to use it. And I structured mine going from k is equal k from k going to 0. So that's why I did 0, 0, k. You could go the other way around with 0, 0, 0, right? Of used instead of how many left. It just depends. It doesn't matter. It's symmetric, right? It doesn't matter. And so given this part, I also have this thing. The idea here for me is keeping track of the cells. Given all the cells, I put it in a list of cells and I sort them, right? So we have a list of cells sorted by the grid value, which is the things that enables you to teleport. And on that, I do a queue, a list of a queue. So we have actually k plus 1, but k plus 1 queues, each letting each sorted by grid sub ij, letting us know what is possible, right? Or what we haven't considered yet, right? And because each cell, the idea here is that because each cell can only be dequeued once, you only check each cell once per call, technically, right? Because you could get rejected, but rejection ends the loop as well, as you'll see later. So it is just all times c plus r times c, so it just becomes 2 times r times c, which is fast enough, right? Okay, and this is standard Dijkstra theory now. I keep on saying standard theory because that's what people say in chess, and I've been watching too much chess stuff. I don't even play chess. I just enjoy people talking about it. But anyway, this is heap. The way that we have it is the cos, or distance, right? Distance or cos, whatever. X, Y, and the k left, right? K left, if you want. So that's the heap, and we sort by the cos because it's Dijkstra. Directions, we want to go down and right. This part is straightforward. And yeah, and then basically you have, like I said, mostly standard Dijkstra. You have to practice if this is difficult. At least most of it. We'll go over the difference, like I said. This is a heap. This is a heap pop to get the lowest cost. If we haven't visited, or if we already visit this, then we skip, because if we already visited, then the cost will be lower. And if it's not, you go to D, that means we've already visited this. And then we continue. If this is the end node, return the result, right? If you're at the lower right, like I said, this is Dijkstra, this is greedy. If you're at a node, that means it's the earliest you can visit it, is the cheapest cost, return D. We have dx dy. You know, this part is straightforward Dijkstra, right? You just go down, you go right, we check both those places, and yeah, this is the cost of the movement, which is grid. Yeah, and then if this is good, it gives you an improvement. Push it to heap, you are bueno, you are good, and yeah. So this is the difference that makes it short enough or quick enough. If you have enough K left, remember, for me, I count down. Maybe I think sometimes, or very often, I count up. I don't know why I count down this time, so that's why I'm putting an emphasis on it. I don't know. It doesn't really matter, like I said. But anyway, while this is greater than 0, that means that we have teleports to use. We just look at the beginning of the queue, right? And that's it. This is an optimization. Let's just skip this for now. But yeah, we look at the beginning of the queue, and because this is sorted, we go, okay, well, grid of X, Y. We look at the beginning of the queue. If it's still in queue, that means that we haven't processed yet for this K. And remember, we have a different queue for each K. We haven't processed yet for this K. So let's process it. That's it. And once you process it, we never process again for that K value, right? We process the NX and Y, we pop left, and then this is just the math, right? Because the cost is 0, we just go, well, if we use this K, it's better than the XY, yeah, then we just update it, we push it to heap, and we are, and so far, that's it. This is still standard Dijkstra without the comment. We'll talk about that in a sec. This is still standard Dijkstra once you understand the queue part of it. Like, once you're given this as an input, this part is standard Dijkstra, right? This, I think I might have even copy and paste from this, but like either way, it is mostly mentally copy and paste in either case, right? This is the new states, and yeah, and you burn up one of the K's, which is why you have the -1, and put everything in heap the same way, right? And that's it. So this ended up taking about 9.6 seconds, still AC, still accepted during the contest, still the same complexity. But the reason why I wanted to optimize it a little bit is because it took 9.6 seconds. I thought there are probably obvious optimizations. The quick one I noticed for optimization is that you could teleport back and forth through all the Ks, right? Meaning if you have one cell that has a value X, and then you have another cell that's value X, you can go back and forth. So this graph is not, it is asymmetric, but you're visiting all the cells, that doesn't make sense, right? For example, if you could teleport downwards, you teleport up because they have the same grid value, and because for this problem, you can't teleport to the same grid value, you'll just go back and forth, right? But if you also kind of think of it in a human way, if you go back and forth, you're probably not taking the shortest path. right? Because if you're going back and forth, you could get further with the same number of teleports. It is technically correct, but you just have to do more updates later, right? Because then now your heap gets bigger, you do more updates, technically I guess your heap just gets bigger, but you also do states that, like, you assess states that would never give you the best answer. Because for example, another example, if you're at a location 2-2 and you have 10 teleports left, and yeah, sure, maybe if the cost is so low that is also your best location at 2-2, if you have like 5 teleports left, right? Maybe it's true, but it also never gives you the best answer to the corner, right? Because you just have 5 fewer teleports, literally, right? So that's basically the idea. But because of this, what I call ping ponging, because you going back and forth, and now you're like doing a lot of math with those states that won't give you the best answer anyway. So I'm gonna just shortcut this by having this here of, okay, if you could get here to the k in if this is your best idea in 10Ks, then it also is your best move at 9K, 8K, 7K, 6K, 5K, dot, right? Because you're not going to get better. And what this does is just that it just allows you to skip putting them in the heap. And so in future if statements, right? In future if statements, it just won't process those nodes, and that's it. And by doing so, it reduced my thing to 5 seconds from 9.6 seconds, right? And that's it. With a very short idea. And I don't know how long I took. I guess it's 8:13, right? I did this in 3 minutes, and it saved 5 seconds, right? And if I was like worried about running time, or if I timed out, I would have probably done something like this just to test. But yeah, and that's it. Otherwise, yeah, because of this while loop and everything gets amortized. Like I said, everything gets amortized. So this actually, maybe surprisingly, maybe not, has the exact same complexity as a normal dice draw. Of course, that's more states. So it depends on what you mean by normal dice draw. What I call normal dice draw is V times log Y. But in this case, V is R times C times K. And Y is also R times C times K. But because we don't do the explicit graph, Y is what you reduce. Y is not V square in a good way, right? So yeah, so that's basically it. Let me write that out, right? So this is still all V log E, but with implicit edges, better implicit edges, Y is equal to yeah, because technically it is this plus V plus Y. I mean, V is dominated, but you always have to look at every edge. But Y is going to be, I guess I don't always point it out. Maybe I should though. That's actually a mistake on my part. But anyway, because Y could be V square, and then that's your, yeah. But yeah, where V is equal to R times C times K. Y in this case is also R times C times K, because now you can think of another way to think about it is that for every node being R times C times K, you only get one incoming match to it, right? Because once you use that one incoming edge, it gets dequeued, and then you have no more edges incoming. So as a result, you can amortize that and say edges is E times K. And that is the heart of this problem. That is what this problem is asking, is that without, this idea, Y would have been, times K squared, right? If you're not careful. It's either I don't know. Let me see. Yeah, I think that's roughly right. Yeah, because you have to do it for each K too. I was debating whether this should be within only these two, but I think this is right. Either way, you reduce it to here, and that is the core part of the problem. And that's it. That's all I have for this one. Let me know what you think. We'll show you the code again. Yeah. Oh, I guess plus you. I guess I messed up actually. Plus relog re. But I mean, relog. This is relog. Oh, sorry. Ye log ye. No, this is re. Messed up. Relog re. Right? It's this sorting. But it gets dominated by this, so I guess I didn't really mess up that much. Yeah. And technically, ye is not this precisely, just to be clear. Ye is like 2 times this because you could go down and right and 1 more maybe for incoming edges. But yeah, but still all of this, right? And yeah, you have cells, sort, you have Q. This part is Dijkstra once you realize it's X, Y, and K. Direction is just the dx dy. This part is standard Dijkstra theory. Standard Dijkstra theory. This Q part is the heart of this problem. Should not have taken me, I don't know, as long as I did, but either way, keep track of CK. Back to standard Dijkstra, knowing the X, NX, and Y, and the CK burning one of them. And then if we cannot visit the last cell, I feel like you always can, right? I just kind of return -1. Yeah, I think you could always do it with this problem because it just be expensive. We could always do it, but I just kind of write -1 anyway by muscle reflexes, I suppose. But yeah, that's all I have with this one. Let me know what you think. Thanks for watching, and yeah, you can watch me solve it live during the contest now. Yeah, much easier. I mean, it took me 22 minutes to try to figure out that one and 4 minutes on this one. How much time do we have left? I guess an hour. Right, we have 29. We're at 29 minutes. Already. All right. 500 people solved this, so we'll see if I can be one of the 500-ish. All right. Again. All right. Let's just wait. All right. Top left, go to bottom right, straightforward so far, normal move, down and right, just like regular DP, teleportation, IJ, such that grids up, oh, we have a grid. So basically the idea is that you cannot construct this graph, oh, maybe, well, you still can't, because that's what, 6,400, so you do that square, that's 880 to the 4th, which is probably too big. So you can construct all this graph together, right? Otherwise, it's just regular Dijkstra. But you got DP. And DP doesn't work directly. Maybe it actually. I think DP works, but you have to be careful of the edges. Okay, so it's just about trying to figure out how to do the implicit graph in an efficient way. DP is on X, Y, and K. Well, no, you wouldn't do a DP. You still do Dijkstra. Fine. Okay. So Dijkstra again. That's a little bit. I mean, because we did Dijkstra for Q3. No, you still do Dijkstra. Okay. I think Dijkstra is fine. You have X, Y, K. The states are fine, and K is 10, so it's not even that big. But then the question is, how do you figure out how to get to all the other places? Well, teleport. Oh, you have to sort grid, right? Some sort of like union find E things, right? So you go from. Okay, so you go from a smaller or equal to number. The thing is that if you're the current cell, okay, it's not that intractable, because the thing is that you would only, in a Dijkstra kind of way, everything is greedy, so you would maintain all the cells that you can go in things. I think about this, because basically you want to amortize it out, so because you never visit but it's like a 2-pointer thing, right? So you use a Q for each one. 80 times 80 times K, that's the number, well, you have K queues, each one with all the cells sorted by the cost, and then you just kind of pop it off the beginning, depending on your current K. Okay, that sounds reasonable. Okay, yeah, I mean, how much time do I have? That took only 3 minutes to figure out. The implementation may be tricky, but we spent only like 4 minutes figuring about it, so not so bad. Okay, yeah, I mean, implementation may be tricky, but yeah. Okay, yeah, so okay, yeah, okay. Okay, yeah. So let's just say cells. So for I in range of for J in range of C, we want to say cells dot append grid ij. Yeah. I mean, I think the reason why I'm thinking is that I don't remember if I can just do this for this one, right? Like, does that make a copy of the tuples? I hope so. We have to test that. I actually don't know that I know. Maybe this is fine actually. I don't know if it's K or K plus 1, so let's just do K plus 1. Yeah, and then maybe I would say Q of 0 dot pop left, and then now print Q is equal to Q of 1, right? It should not be if this is correct. So okay, so it's false. Maybe we can print it out real quick. Oh, well, that's I messed up. Should be this, but we can print this. I just want to see if they overlap in memory, because it's a very easy mistake to make. And I am a noob. Okay, so yeah, it looks okay. I forgot to sort though. So, but that's fine. Yeah, let's see. Yeah, okay. So this is after the first one it pops. Okay, so this is what we want. Okay. How did that take 3 minutes to write? But okay. What am I doing? Okay, I have to double check whether I want it forwards or backwards. That's what I want to do. I need like a to-do list. Okay, because we can go to the smaller ones. Okay. So that's fine. Yeah. Okay, so we're good. We're Gucci then. Then yeah, this is just literally the same code as Q3. Not literally. But we have best if you go to times C for K plus 1. K plus 1. Maybe. No, I think it's K plus 1. It's fine. Yeah. Okay. And then we'll write it backwards, and best of 0, 0, we have K moves, or K teleports is equal to 0. Set up a heap, and we want to put cost 0, 0, 0, K. What is the tiebreaker? I guess it shouldn't matter. Okay, yeah, okay. Like, I wonder if there's a tiebreaker that I need to care about. Maybe I'm wrong on this one, but anyway, D, X, Y, K, current K just in case. Okay, and then if best of X, if X is equal to Y, oh, nope, minus 1, and Y is equal to C minus 1, then we return the D. Actually, I guess maybe this. I mean, it's greedy. I don't think it matters, but I sometimes it's a little bit more particular. Okay, so then now this is straightforward up. Or not? It's not up, down, left, right. You know it. Honestly, the funny thing is that it doesn't even matter. I don't. Yeah, okay, this one can go to any distance, not just up, down, left, right. Okay. Huh, that is interesting though, actually. Hmm. Right, so you have someone like that, right? So you have for dxdy and pretty. This part is pretty straightforward. Or I've done this maybe a million times and I still get it wrong all the time, but still should be pretty okay. Okay, ck remains the same, so it is going to be best of nx and y ck. If this is greater than best of, technically just the d, right? Yeah, d plus, I don't like it right with d though, because sometimes I mess up. ck plus 1, then oh, the cost of teleport is 0, so you could, it's like actually I messed up a little bit. I use heap. This could be a 0, 1 q. Do I want to change? I mean, I'm gonna write it this way because I'm a little bit too late to change. But let's put a note. Technically on the heap. I mean, it's not too late to change, but I don't want to rethink stuff. The only thing I worry about is that it might time out. But yeah, okay. So right. One, and then I maybe I could have thought about it a little longer, I suppose. Yeah. Okay, and then now we have to do the thing where yeah, while length of q of the current k. Yeah, I think that makes sense. Yeah, and the cost is 0 anyway. So maybe I did this. I don't know. I didn't really think about the. Yeah. I thought that. Yeah, I don't know. I just didn't think about it too much, honestly. Okay, so the previous cells. Oh, that's the grid x, y. So while this is less than or equal to, so we did. No, what are you doing? Well, the value is on the q, but maybe that's fine. I don't know. I like to reuse things on the source, but grid of xy, then q of ck dot pop left, and then we do best of nx and y, or not nx and y. Okay, so nx and y is equal to q of ck of 0. Oh, we have to do this before we pop. And the first is the d, or the grid thing, which we don't care about. We pop left, and then now it is just the same thing as before. We just do. This part I'm going to copy paste. Okay, right, and then that's it. Return -1 if we never reachable. Is it always reachable? I guess it should be always reachable. Yeah, okay. Int does not support. Did I mess this up? Best oh, oops. Tuple and int. Tuple and int. Oh, wait, no. This is a tuple. Oh, yeah, of course it's a tuple. It's the beginning of the queue and then the first item on the queue. Where am I failing? 36. Oh, wait, oh, C and C. Oh, I didn't bounce. Also, I messed it up. I count up. So I am messed up. Also, I never update CK, so I'm just way messed up. This is right. Actually, this part is fine. Then why is it going out of bounds, actually? I never update CK, which I should, actually. I messed that up. But let me write a thing. CK. But I want to debug why this goes out of bounds first. C. Huh? Why it goes out of bounds? The current K is going to be K. We have K plus 1. Oh, I did my indexing backwards. Okay, I am done. Okay. Whoops. Okay, maybe it's easier to just rewrite this part because I did intend it deep. It also be okay. Okay. We have 3, which is wrong. Oh, because we didn't update K. That's probably why. Okay, but at least it didn't crash. So then now, if CK plus 1 or minus 1, and because we want to go right. We also want to check if CK is greater than 0 because we don't want to go to the negatives. Okay, we still this is still 2. Why is it 9? Oh, did I get the cost wrong? The cost is the okay. So that sure is actually reasonable now. Okay, the cost is I also added plus 1 for some reason, even though it said it is free. So okay, so that part we can make cheaper, but then now we have to make this part the destination cell, so grid of n, x, and y. We have to update this. So okay, easy fix, and luckily we didn't need. Well, I don't know. We don't have to use 0, 1 grid, which okay. Remove that comment. Pretend you didn't see that. We have 9. Oh no, that's for the second one. 14 and 9. Why 14? Dun dun dun. Do we also start at cost 1? No. So we move down, 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 ooh, down again, or to the right, which is 5, okay, and then teleport to there. The cost is free, but it just needs to be okay. That sounds right. Just double checking my things. Very easy to make a typo. Alright, let's print it real quick. Okay, 0, 0. CK is okay. We have 2 moves left. We go to the same spot, but 1 move left and then same spot. Okay, so I'm guessing that this part it activates itself, which is fine maybe. But then now it goes to 1. It should go to down, so 1, 0, with a cost of 2, which is true. 14 is way too high, and then it should go to the right, so 1, 1 should have a cost of 7, which is right. But this goes to 14. Why? Alright, let's see what this part is doing. Am I doing it wrong? Connecting CK, XY, NX and Y. Okay. So 1, 1 should connect to 2, 2. So 1, 1, 2, 2. Did I mess this up? No, this is should be right. Oh, this is -1. Okay. I guess I missed a -1. Okay, 7, 9. Okay, let's remove some print statements. There was one more, right? Okay, there. I forgot I should use this. 7 and 9. All right, let's YOLO. I mean, overall, I guess if we time out, that'll be a little bit sadder. But not too bad. I think there is an optimization I can do. Oh, 9 seconds, a little bit tough. But we got it, so whatever. Doesn't matter, AC, right? All right, I mean, not too bad. An optimization is that you would also, the queue, like if a cell is, I don't know if that's true actually. I don't know. Like I mean, you definitely could optimize it so that if you've been into this place, like if you've been here in fewer steps with more CK, then you could like eliminate some stuff or something. But I don't know that. But it's fine probably. It is very tight though. Can I do a little bit better? I think these things you could maybe change it to be a little bit better. Because the thing is that this makes it so that you teleport back and forth a little bit. Which makes it visit all the states. I mean, we're done, by the way. But I'm just trying to think. Maybe 9.6 seconds is a little bit scary. I don't know, what's the max one time? It used to be always 10 seconds on Leetcode. I don't know anymore. But there's this like ping-ponging, teleporting thing where it just goes back and forth, which is not what you want because it visits all the states. Even a lot of states that won't give you the best result necessarily because you've been running back and forth unnecessarily, right? Like you could get to the end with 0K or something when you could have also gone there in less time or some or less K. But I don't know. I'm still trying to think a little bit. Like maybe like here, maybe we can write something like, I don't know, just to speed it up. And I don't know that this is quite great, honestly, but maybe like, I don't know, NK is equal, CK -1, -2 maybe, all the way to 0. We just kind of hacked this to be this, right? And it will prevent a lot of random states from happening, right? Let's see. Like maybe it'll get, I don't know, maybe it still kind of happens, but you could see that at one time already cuts by half because we just cut off a lot of states. So okay, like if I had 5 seconds, I would have been pretty happy. And this isn't quite thing because there is some like symmetric thing, but so I gotta stop running money. But yeah, I mean, with 5 seconds, I am much more comfortable and happier. Because these are all basically what we're doing here is that we're saying all these things are not possible, or maybe we just kind of already did it, right? Like you could, like I said, you're just trying to get rid of the case where ping pongs back and forth, and as a result, you visit so many states in a way that doesn't really change anything, or won't give you the optimal result that you cannot get in a normal way. But yeah. Anyway, cool. That is all I have with this one. Let me do a quick retro. I mean, Q2 for me was the hardest one, because I was just struggling until I got it. And once I got it, it's not so bad. Obviously, with you could see the for loop, and it's kind of the pattern was kind of obvious once you look at the thing. I don't know, but was it even my longest problem? I think it is. Q3 was 4 minutes. Q4 was less than 20 minutes. So Q2 was definitely my hardest problem. And I didn't look at the name, so I was I just kind of assume everyone on top cheated, but I would not assume KMJP cheated, so maybe I could have looked at that for inspiration. Definitely very quick though. I mean, I'm not surprised Q3 was quick for him, or Q4 really. Like I got the idea and like pretty quickly. Oh, I didn't know you could click on it while I have a contest going on. Very weird design decision by Leetcode. But in any case, yeah, I wouldn't expect him to be cheating. And so finishing 4th is very, very impressive. Yeah, but also like not surprising. Like probably just, yeah. Oh, I actually did it do it with DP. Huh. Don't know what to say. I mean, maybe his DP does look a little bit different than how I structured it. And maybe. Thanks for watching, everybody. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem, this contest, everything in between. Stay good, stay healthy, take good mental health. I'll see you all later and take care. Bye bye.